Hi. So I'd like to talk to you today about the fundamentals of some circuits, and in particular we're going to focus in on RC circuits. So first of all, what do I mean by RC circuits? Well, we're going to cover direct current circuits specifically, so the current is going to be flowing in one direction only, and we're going to focus on circuits that have both a resistor and a capacitor, and perhaps in addition a battery and a switch. Okay? So previously we've been just looking at batteries combined with resistors or batteries combined with capacitors. But if you have an RC circuit with resistors and capacitors, you introduce some time dependence, and we're going to go over that. Okay, so first of all, let's assume that you have a battery with some EMF and you hook it up in a circuit with a switch, a resistor, and a capacitor. Now at time t is equal to 0, you close the switch and current begins to flow in the circuit. So the current flows through the resistor and then to the capacitor. The capacitor we're going to assume is initially uncharged, and so as soon as current begins to flow, the charge begins to build up on the capacitor plates. In this case, the current is flowing such that it's flowing towards the positive plate of the capacitor. Remember that the definition of current is the direction of positive charge flow, and so the positive charges are going to be pushed to the positive capacitor plate. But since the capacitor acts like an open source, the positive charge must build up on that positive plate, and that induces a negative charge buildup on the other side of the plate. Okay? Now, what's going to happen is that as long as that switch is closed, the capacitor is going to charge at a rate that's kind of governed by what the resistor is. The stronger the resistor, the slower the capacitor will charge, okay? And it's going to continue to charge until it reaches its maximum charge. The maximum charge that the capacitor can hold is given by the equation for capacitance, right? So we still have that C, the capacitance, is equal to the charge divided by the voltage difference between the plates. But now for the max charge, you're going to rearrange that equation, and you get that Q is equal to C times the EMF of the battery that it's hooked up to. Okay? So once the capacitor is fully charged, the current in the circuit will go to 0. Okay? Current will no longer flow. And as the plates are being charged, the potential difference across the capacitor is going to increase until the potential difference is equal to the voltage on your battery. Okay? Once that maximum charge or that maximum potential difference is achieved, current in the circuit will stop. Now, if you look at what the flow of charge looks like through the circuit, you're going to see an exponential increase of the charge building up on the capacitor plate. So it starts out and it builds up at a very rapid rate when there's no charge initially on the capacitor. But then as it starts to reach its maximum charge, it's going to slow down in its growth until it approaches that asymptote, and the asymptote will be the max charge on the capacitor, C times the EMF of the battery. So if you were to write an equation for that, the charge on the capacitor as a function of time, little q of t, is equal to the max charge on the capacitor, which can be expressed as C times the EMF, times 1 minus e to the minus t over RC. Here, E is, 2.781828, right, it keeps going on. T is the time, R is the resistance of your resistor, and C is the capacitance of your capacitor. Okay? Now, if you want to solve for what the current in the circuit is, remember that the current is just defined as dq dt. So you take the derivative of that expression that we have for the charge buildup on the capacitor, and you end up with the current is equal to the EMF of the battery divided by the resistor times e to the minus t over RC. Okay? Alright, so that's the current. So you can see that the current will exponentially decay. It'll start off of its maximum value, which is the EMF over R, and it'll decay off until it reaches 0. And the point at which it reaches 0, of course, the capacitor is fully charged. Now, the time constant is something that we call R times C. As we discussed, R is kind of a governor for how fast that capacitor can charge. And so if you multiply the resistance R times the capacitance C of your circuit, you'll get the time constant. The time constant represents the time required for the charge to increase from 0 to 63% of the max value. if you do multiply resistance times capacitance, you do get units of time. A lot of students are, surprised by that, but you should go through the dimensional analysis as a nice exercise. Now remember that you can also speak of the potential energy stored in a capacitor. We covered this in a previous lecture. So if you have a energy stored in a capacitor, you can say that that's 1/2 times Q times the voltage across the capacitor plates. Or you could express that as 1/2 times C times the voltage across the capacitor plates squared. Okay? Now this is also going to be a function of time. The expression for the max is shown here though, so the max energy stored in a capacitor. Alright? Let's do an example problem for a charging capacitor. Let's have a 6-volt battery of negligible resistance used to charge a 2 microfarad capacitor through a 100 ohm resistor. We're going to find the initial current, the final charge on the capacitor, and the time required for the charge to reach 90% of its maximum value. Okay, so let's look at those equations that we already talked about. Your current, I of t, is the EMF over R times e to the minus t over RC. So now plugging in for R values into that equation, we have the EMF over R is equal to 6 volts divided by 100 ohms times e to the minus t over RC. Well, the max current will be the current when t is equal to 0. And then that exponential, e to the minus t over RC, that will go to e to the 0, which is 1. And so that means that the coefficient that multiplies your exponential, 6 volts divided by 100 ohms, is your max current, or 0.06 amps. Okay, next it asks for the max charge on the capacitor. Well, that would be as time t goes to infinity and it's fully charged. So you would just multiply the capacitance C times the EMF of the battery. In other words, it would be like the resistor wasn't even there and you're just using the equation for capacitance. So that would be 2 microfarads times 6 volts, which would give you 12 microcoulombs. Now, I find it useful to calculate the time constant here, even though the problem didn't explicitly ask us for it. Tau is equal to RC, which is 100 ohms times 2 microfarads, and that gives us a time constant of 200 microseconds for this RC circuit. I'm going to plug that in to our equation for the charge. Q of t, or the charge as a function of time, is going to be Q times 1 minus e to the minus t over RC. Plugging in for the values that we already have, you could say that 12 microcoulombs would be the max charge, that would multiply out front, times 1 minus e to the negative t over 200 microseconds, our time constant. Okay, well, we want to charge it to 90% of our max charge. So to do that, what you're going to do is you're going to divide both sides by the max charge. So if you have 90% of the max value, then whatever your charge is at that time divided by 12 microcoulombs has to equal to 0.9 because it's 90% of the max. So I just divided out by that 12 and then called the stuff on the left-hand side 0.9 because it's 90% of your max. That would then equal 1 minus e to the minus t over 200 microseconds. Okay? If you don't quite get how I got to this point, I think it's worth it to pause the video and think through why the left-hand side of that equation would be 0.9 at 90% of the max charge. So pause it now if you need to think that through. Otherwise, I'm going to continue. So now my equation is 0.9 is equal to 1 minus e to the minus t over 200 microseconds. Rearranging that equation a little bit, okay, I'm going to take my exponent over to one side and then put everything else in the other. I get 0.1 is equal to e to the minus t over 200 microseconds. To get rid of that exponential, I'll take the natural log of both sides. When I do that, I end up with ln of 0.1 is equal to negative t over 200 microseconds. But because I'm not going to have a time that's before t is equal to 0 and all that good stuff, and the natural log of 0.1 is a negative number anyway, I'm just going to move that negative sign to the other side, and then I have minus ln of 0.1, right, which will give me a positive number, is equal to t over 200 microseconds. Solving, plugging into my calculator, I end up with t is equal to 460 microseconds. So that's how long it takes the capacitor to charge to 90% of its max value. Okay, now let's discuss discharging a capacitor. Let's say that you have a capacitor that you've already charged up with a battery or something, and so it's sitting there at its charge. And then you're going to use that as a power source for some external load with resistance R. So you're placing it in the circuit, okay? When you place it in the circuit in series with a resistor and close the switch, what happens is current begins to flow. Since the current is defined as the direction of positive charge flow, it's going to flow away from that positive plate. In other words, the positive charge would like to move towards the negative charge because it's attractive, but it can't because there's an insulating material in there. So in order to meet up with the electrons and make the total net charge zero, it's going to flow counterclockwise in the circuit. Now, because we already defined the definition of positive current here as flowing towards the positive plate, we're going to call this current negative in direction because it's flowing away from the positive plate. Okay? Alright, so we have our current flowing counterclockwise through our resistor, and eventually our capacitor will discharge completely, and the charge on the capacitor plates will go to zero. So this charge is going to decrease exponentially. The equation for that is the charge on the capacitor plate at time t, Q of t, is equal to whatever the max charge on the plate was at t is equal to 0 times e to the minus t over RC. Here, t is the time, and R and C are the resistance and the capacitance, respectively. Now, the current can also be found if you take the time derivative of that equation. I would then be dq dt, which would be minus q over RC times e to the minus t over RC. So here's that negative sign, okay? The negative sign, though, it just indicates the direction that current flows. In other words, it's flowing away from the positive plate of that capacitor, okay? Alright, so that's our expression for current. Here, since our charge on a capacitor plate is decreasing, both the magnitude of the current and the magnitude of the charge decrease exponentially. So at our time constant, tau is equal to RC, the capacitor has lost 63% of its initial charge. So both the charge and the current decay are characterized by that time constant. Let's do an example problem for a discharging capacitor. We have a 4 microfarad capacitor fully charged with a 24 volt battery, and then we disconnect it from the battery and instead connect it across a 200 ohm resistor or external load. We're going to find the initial charge on the capacitor, the initial current through that 200 ohm resistor, the time constant, and the charge on the capacitor after 4 microseconds. So here we go. So the max charge on the capacitor plate would be equal to C times the EMF of the battery that it was hooked up to. So that would be 4 microfarads times 24 volts, which would give me 96 microcoulombs for the initial capacitor charge. I of t is equal to minus q over RC times e to the minus t over RC. So that would be equal to negative 96 microcoulombs divided by 200 ohms times 4 microfarads times e to the minus t over RC. Yet again, the max current is going to happen when t is equal to 0, or at least the max magnitude of the current will happen when t is equal to 0. And so if we plug in t is equal to 0, that gives e to the 0, which is 1, and so we end up with minus 0.12 amps. So the coefficient that multiplies the exponential is the max current, which in this case is minus 0.12 amps. Now yet again, the minus sign just indicates the direction, so that means it flows away from the positive capacitor plate. The time constant tau is equal to RC, which is 200 ohms times 4 microfarads, or 800 microseconds. Now, our expression for Q of t says Q of t is equal to the max charge times e to the minus t over RC. Plugging in for the numbers in our equation, we have 96 microcoulombs as the max charge times e to the minus, t is 4 microseconds here, divided by the time constant, which is 800 microseconds. Plugging and chugging in our calculator, we end up with 95.5 microcoulombs as the charge on the capacitor at time 4 microseconds. Okay, so that's a little sum up of RC circuits. Let me know if you need anything, and I'll see you in class.